This lecture will be about Chapter 3, Acids and Bases. So we're going to start off with 3.1, the Bronsted-Lowry definition of an acid and a base. So an acid is a proton donor, and so this means that it's going to donate H+. And a base is a proton acceptor. Okay, so a base will accept H+. And when we do a reaction, it's a proton transfer reaction. So here, if I give you an example, we have HCl and we have water. Okay. Alright, so let's just put the lone pairs here in. Here is our acid. It donates its hydrogen to water, which is the base. And we are left with Cl- and H3O+. Okay, the Cl- is the conjugate base, and the H3O+, is the conjugate acid. Okay, if we just do another example of a Bronsted-Lowry reaction, what we can see Right, now if we look at this here, we have a base. It's going to accept a proton from water, which is our acid. We make an alcohol, which is the conjugate acid. And we make OH-, which is the conjugate base. So in the first example up here, we had HCl acting as the acid and water acting as the base. In the second example, we have an alkoxide, which acts as the base, and water, which acts as the acid. Now, what we can do is we can use curved arrow notation to look and follow the flow of electrons. Generically, what we can do is we can write B-. Okay, so here's our acid, here's our base. So B- will take the hydrogen or accept the hydrogen. Okay, and HA donates H+. When we use curved arrows, we're looking at the movement of electrons. So we only show where electrons are moving. We never show where positive charges are moving. So we can see that the electrons from the base take H+. The bond between H and A is broken, and those electrons go on to A. And we are able to make a conjugate acid and a conjugate base. Conjugate acid, conjugate base. Let's practice drawing curved arrows. So we're going to do Skill Builder Exercise 3.1. And what we need to do is to show the mechanism for this proton transfer reaction that I'm drawing here. Alright, first thing, this is water, this is methoxide, this is hydroxide, and this is methanol. Now, you can see here that water is the acid. It's going to donate H+. Methoxide is the base. It will accept H+. So in order to draw the mechanism, we're going to show the movement of the electrons. The electrons from the base take the hydrogen, you break the oxygen-hydrogen bond, and the electrons go on to oxygen. And that's how we form hydroxide, which is the conjugate base, and methanol, which is the conjugate acid. Now, let's move on to section 3.3, and we're going to evaluate the strength of Bronsted-Lowry acids based upon quantitative measures. In order to evaluate the strength of an acid and a base, we look at the equilibrium concentrations of the various components, and we look at the equilibrium in water. So we evaluate what is the propensity of an acid to donate a proton to water. Okay, so if we look generically, we have HA plus H2O will yield A minus plus H3O plus. And if we were to draw, if we were to express the equilibrium constant, it would be KEQ equals A minus times the concentration of H3O plus divided by the concentration of HA times the concentration of water. Now, when we're looking at acid-base equilibrium, typically we define it as the acid dissociation constant, or the Ka. And we can ignore water because water is constant, and we can rewrite the equilibrium expression to be the concentration of A minus times the concentration of H3O plus divided by the concentration of HA. Okay. A very strong acid has a Ka that is on the order of 10 to the 10. Pretty much strong acids have a Ka greater than 1. Weak acids have a Ka less than 1. Often what we will do is we will use the pKa to evaluate acid strength. And the pKa equals the negative log of the Ka. When we do this, okay, typically pKa values will range from negative 10 to 50, where each unit change corresponds to an order of magnitude. So for example, if you have an acid that has a pKa of 10 and another acid that has a pKa of 16, then the one with the pKa of 10 is 6 orders of magnitude or 1,000,000 times more acidic. Okay, so to sum up, the higher the Ka, the stronger the acid. The lower the pKa, the stronger the acid. Please look at table 3.1 for some common pKa values. Let's do an example on evaluating acid strength using pKa's. So, if we have acetic acid and we have acetone, and we look up the pKa values, you'd see acetic acid has a pKa value of 4.75, while acetone has a pKa of 19.2. So acetic acid is the stronger acid, and it is about 14 orders of magnitude stronger. We can also use pKa's to evaluate basicity. Okay? And so, if we look at 3.3, and you have 2 bases here, and we need to figure out which compound is the stronger base. Okay, so let's first write what the conjugate acids of each are. And so we would just protonate each carbon. And if we look up the pKa's from the table, we would get the following values. And so we need to remember that the stronger the acid, the lower the pKa, and then the lower, or the weaker, the conjugate base. So we can see that the first compound has the lower pKa. So it is the stronger acid, and thus will make the weaker conjugate base, making the second anion. If we go back up, nope, can't do that. I'll just redraw it. So this was the second anion. This is the stronger base because it comes from the weaker acid. We can use pKa values to evaluate if the equilibrium lies to the left or to the right. And in order to predict the position of the equilibrium, we are going to favor the weaker acid. So let's look at an example. Okay, so here we have an acid, and the pKa, oops, I have too many carbons in my acid. Let me go back. So the pKa of acetic acid equals 4.75, and the pKa of water equals 15.7. Now, water is a weaker acid than acetic acid, so the equilibrium will be to the right. So always remember we are going to favor the formation of the weaker acid. Right. If we think about ourselves physiologically, okay, we need to look at the fact that the pH of living cells is generally between 7 and 8.5, and this will affect the ionization of different functional groups. And what I mean is are they protonated or unprotonated or deprotonated? Same thing. Now, common functional groups that are ionized are either acids or bases. And so we can be looking at carboxylic acids or typically amines. Now, for rules of thumb, an acid will be substantially deprotonated if its pKa is 2 or more units lower than the pH of the solution. And a base will be substantially protonated if its pKa is 2 or more units higher than the pH of the solution. So let's do some examples. If we were to take glutamic acid, which is one of the 20 amino acids, we would see that it has 2 acidic groups, and then it has an amine. Now, at pH equal to 0, everything is protonated. When you raise the pH to 7, which is physiological pH, you will deprotonate both of the carboxylic acids, so that you get an ion such as this. And we can see that this ion has a negative charge because the amine stays protonated, whereas you deprotonate both carboxylic acids, and so you have a net negative charge. So at pH 7, okay, we can see that we are 2 units above the pKa's of these acidic groups. The pKa of these acidic groups is the following: 2.2 and 4.3. So they are deprotonated at pH 7. The pKa of the amino group is 9.7. Okay, so we are still protonated here. Some other biological groups that we can look at are the phosphoric acids that make up DNA. They are deprotonated and negatively charged. Often different drugs will have different functional groups. And their protonation will depend on the environment in the body. Often, it's easy to recognize an inorganic acid, such as HCl or H2SO4. Organic acids, on the other hand, are characterized by the presence of a positively charged polarized hydrogen. It doesn't have to be positively charged, but essentially you have a positively polarized hydrogen. So let's just get rid of that charge there. And so there are 2 types, where you can have hydrogen bonded to an electronegative oxygen, or a hydrogen atom bonded to a carbon atom next to a carbonyl. So a couple of examples we've looked at Okay, you can have acetic acid. These protons here, they're on a carbon that's between two carbonyls. All right, so you need to have a positively polarized hydrogen. If we move on to section 3.4, we can also look at evaluating Bronsted-Lowry acid strength qualitatively. If we go back to our generic where we have HA, okay, and it can dissociate into H plus and A minus. Now, so A minus is the conjugate base. And what we can do is we can evaluate the stability of A minus. The more stable A minus is, the stronger the acid. It's because if this is stable, then we can have HA dissociate. So the first thing that we look at is the negative charge on A minus. And we want that negative charge to be on the more electronegative atom. So if we compare elements in the same row, the more electronegative atom bearing the negative charge is more stable. So let's compare the following two acids. And so here we have butane. If you deprotonate, you have a negatively charged carbon. If we compare this to propanol, here the oxygen bears the negative charge. Oxygen and carbon are in the same row. Oxygen is more electronegative. So therefore, propanol is the stronger acid. This anion is more stable. Now, if we are looking at elements that are in the same group, so we're looking at columns here, size is more important. So the larger the atom bearing the negative charge, the more stable the anion. So if we were to compare propanol with its thiol counterpart, okay, sulfur and oxygen are in the same group, sulfur is larger, so therefore the thiol is the stronger acid. The reason is that it all comes down to delocalization of charge, essentially. The larger the atom, the more split out the charge. Okay, so when we're comparing atoms in the same group, we are going to look at size as opposed to electronegativity. Next, what we can do is we can look at delocalization of negative charge. I'm going to cross out induction for now and then do that on the next slide. When we're looking at delocalization of negative charge, we're looking at resonance. Can the negative charge be spread across the molecule? Let's compare ethanol to acetic acid. If we were to deprotonate ethanol, we would get the following anion. There is no resonance. If we were to deprotonate acetic acid, here we have the negative charge on the oxygen. Well, we can delocalize that negative charge by resonance so that you have some charge, well, that the charge is essentially spread across the two oxygens. So let me just show you this representation here. So you can think about that negative charge as being delocalized across the two oxygens. So the acetic acid is going to be more stable, is going to be the stronger acid because the anion is more stable. Next, we can look at induction. For induction, I'm going to draw the two examples. So again, we're going to look at A- for acetic acid, and then we'll look at A- for trichloroacetic acid. Same number of carbons. Now the trichloroacetic acid is a stronger acid. But neither of our first factors really comes into play here. In both cases, the negative charge is on oxygen. You have the same number of resonance structures because you can delocalize the charge to both oxygens in each anion. So why is trichloroacetic acid stronger? And what it comes down to is induction. These chlorine groups are electronegative. They can pull electrons towards themselves, and by pulling electron density this way, they can pull the negative charge. This then reduces the magnitude of the charge on the oxygens. Okay? So therefore it makes this a stronger acid because in essence it's delocalizing that charge. There's not as much charge on this oxygen. A key thing to remember about induction is that it drops off the further you are from the negative charge. So, for example, if I were to give you these two acids and I'd say which is stronger, let's draw A minus for both. Okay, so negative charge on oxygen. You have equal resonance forms. Let's look at induction. Here the chlorines, okay, are 1, 2 carbons away from that negative charge. Here they're 1, 2, 3. So the first would be the stronger acid. The last thing that we can look at is percent S character, or the orbitals. So the more S character of the anion, the more stable the anion, the stronger the acid. Okay. When we have an sp orbital, it's 50% S. sp2 is 33% S. sp3 is only 25% S. So that is why when you have an sp3 carbon, an sp carbon, it's more acidic. Okay? S orbitals hold the electrons closer to the nucleus, and they are lower in energy than your p orbitals are. Organic bases, just to add this, they're characterized by the presence of an atom with a lone pair of electrons that can bond to H+. Nitrogen-containing compounds are the most common organic bases. They can accept H+. Before I move on to 3.5, let's just rank the factors we discussed. First comes the atom. Okay, if they're in the same period or row, you look at electronegativity. If they're in the same group, you look at the size of the atom. Next comes resonance, followed by induction, and finally the S character. Let's do section 3.5. And this is looking at the position of the equilibrium using the qualitative descriptors we just discussed. So you're looking at A minus essentially and its stability. So remember, similar to our discussion of quantitative where we looked at the pKa, we're going to favor the formation of the weaker acid. Okay, or the more stable A minus. So let's look at the following example. Okay, so let's compare the anions on both sides, and we're going to favor the formation of the more stable anion. On both of them, we have the negative charge on nitrogen. Here, and we have resonance in both cases. So I'll draw the resonance structures here. Okay, so what you can see is that here we have the sulfur bearing the negative charge, and here we have the oxygen bearing the negative charge in the anions. This is the more stable anion because sulfur is larger. So we are going to favor the formation of this anion. And what you would see is that the pKa of this acid here is actually 24, and the pKa of this acid is 13. So that the equilibrium is going to be more towards the left. So we can think about this in terms of forming either the weaker acid or the more stable anion. Okay. When you're not given pKa's, you can look to see which is the more stable anion, and then you will favor that side of the equation. When you are given pKa's, you'll look for the acid that has the higher pKa, indicating the weaker acid, and you will favor that side of the equilibrium equation. I'm not going to worry about 3.6, even though I discussed it in class. Let's look at 3.7, which is solvating effects. And here we have to consider the ability of the solvent to stabilize the negative charge. And so if we look at T-butanol and ethanol, in both cases you'd have a negative charge on the oxygen. The pKa of terse-butanol is 18, and the pKa of ethanol is 16. And what this has to do with is that when you form the anion, you have a bulky terse-butyl group that prevents water from stabilizing the negative charge. Okay. To the Lewis acid definition of acids and bases. Okay. So a Lewis acid is a species that can form a new covalent bond by donating a pair of electrons. And a Lewis base is a species that can form a new covalent bond. A Lewis acid is a species that can form a new covalent bond by accepting a pair of electrons. A Lewis base is a species that can form a new covalent bond by donating a pair of electrons. And so let's draw the following. We have water and we have HCl. We looked at these when we were defining Bronsted-Lowry acids and bases. And what you can see is that water is going to act as a base and donate a pair of electrons. And the acid accepts. We form H3O plus and Cl minus. Okay. When we donate, the electron pair becomes shared with another atom, and we form a new covalent bond. In this case, it was between hydrogen and oxygen. You can have Lewis acids and bases be uncharged so that the reaction forms a new molecule where the atoms actually acquire a formal charge. So let's look here. We have water. We have BF3. The water can donate a pair of electrons to the boron. Now the oxygen has a formal positive charge and the boron has a formal negative charge. As I showed above, a proton transfer reaction can be considered from the Lewis acid base description. That's where we looked at HCl and water. When we talk about aromatic compounds in the spring, we'll look at BF3 and AlCl3. They can accept electrons readily. And so also, the Lewis definition of acids and bases is more general and includes Bronsted-Lowry. Bronsted-Lowry is only protons being transferred, whereas Lewis can encompass both protons and electrons by definition. So that concludes our discussion of Chapter 3, Acids and Bases.